Hi everyone, thanks for joining. This is joint work with Vasilis Gkatzelis of Drexel University and Nisarg Shah of the University of Toronto. So this paper is generally about voting theory, so I'll start by introducing the general framework. So in the framework, there'll always be a set of voters, and this talk will always be labeled by the numbers 1, 2, 3, and 4. And these voters have preferences over a set of candidates. Candidates here will always be labeled by the letters A, B, and C. And these preferences are ranked in the sense that voters tell us they're ordering over the candidates. So the way to interpret this is that voter 1 prefers candidate A the most, followed by candidate B, followed by candidate C. These preferences are fed into what we call a voting rule, which then chooses and outputs a single winning candidate, in this case, candidate A. In this talk, I'll mainly be focusing on deterministic rules, so we can really just think of this voting rule as a function. It takes a preference as input and outputs a winning candidate. Now, the classic literature has mainly focused on what axiomatic guarantees can voting rules satisfy. These are things like Pareto optimality and strategy proofness. However, also in this literature, there are numerous impossibility results, which show that certain sets of axioms are simply incompatible with each other. There is no voting rule that satisfies all of them at the same time. And this can make it difficult to compare voting rules, because if they satisfy different incomparable sets of axioms, there's not a clear way to tell which one's actually better. So this led computer scientists to introduce a more quantitative framework, another way to analyze voting rules. This was first introduced by Prakacha and Rosenshine in 2006, and then this more restricted setting was introduced by Ancelovich et al. In 2015. So the idea is that these preferences aren't arbitrary. They're induced by, in our case, costs that come from a metric space. So the way to think about this is this metric space can represent voter and candidate ideologies. So the closer a voter is to a candidate in this space, the more similar their views are, and the more that voter prefers that candidate to others. So the way these costs induce the preference is that voters simply say they prefer candidates that are closer to them. So voter 1 here says that they like A the most, followed by B, followed by C. And these costs give us a quantitative way to analyze chosen candidates. So when we choose candidate A, we can simply look at what is the total cost, like the sum of the distances from voters to candidates, to that candidate, and then compare this to other possible candidates. So our goal here is to minimize this total cost. However, since the voting rule doesn't actually see the metric space, it's only given as input the preferences, it may not be possible for the voting rule to exactly minimize this objective. Instead, we might hope that it could approximate this somehow. So why is it reasonable to assume that voters and candidates exist in a metric space? I'll give you a few examples from politics that I hope show how general this framework can be. So the most basic setting is simply a metric space that's a line. And in politics, we can interpret this as the left wing and right wing line. So it's reasonable to assume that voters and candidates are somewhere on this line, and voters prefer candidates that are closer to them. Now you might complain this is a bit too simplistic. So you may have seen these online, call this a political compass. This is a two-dimensional metric space, and the dimensions here correspond to your economic views and your social views. And again, it might be reasonable to assume that voters and candidates exist somewhere in this space, and that voters prefer candidates that are closer to them. Now, even this might be a bit too simplistic. So political scientists have analyzed what they call the Downseam proximity model. And one way to interpret this is that it's a high-dimensional metric space where each dimension is a different issue. And again, the more issues that a voter aligns with a candidate, the closer they'll be. But we allow arbitrarily complex metric spaces here. So let me just give you the formal framework. So we'll have a set of n voters and m candidates. And then we'll have some metric over the voters and candidates. So some distance function d that importantly satisfies the triangle inequality. And these distances induce what we call the preference profile. This was simply what I was calling the rankings before. And it does so in the natural way, where voters prefer candidates that are closer to them. And if there's a tie in distance, we allow for arbitrary ranking. A voting rule F takes this preference profile as input, and outputs a single winning candidate. Now the metric also gives us a way to talk about the cost of a candidate. So we'll say the social cost of a candidate A is just the sum of the distances from that candidate to all the voters. And now we're analyzing rule F. we can look at this worst case approximation ratio. Since f only takes as input the preferences rather than the whole metric, it may not be possible to always get the best possible, to choose the best possible candidate. So instead, we look at this ratio. In the numerator here, we have the social cost of the candidate actually chosen by the rule f. And in the denominator, we have the social cost of the best possible candidate. Then we look at this in the worst case overall instances. In this literature, this is often called the distortion of rule f. And note that this approximation ratio, it's not due to any computation or complexity issues, but rather it's due to the lack of information. So f only has the rankings of the candidates by the voters rather than the full metric. So natural question then is, what is the lowest possible distortion? So I'll go over some selected prior work, and this is just an analysis of many different well-known voting rules and their associated distortion. So in 2015, when Incelovich et al. First introduced this framework, they showed that rules like k-approval actually have unbounded distortion. So this approximation ratio not bounded by any number, but more common rules like plurality and board account have distortion that's actually linear in the number of candidates. Even this year, there's been more work on this stuff. So David Kempe showed that two rules, rank pairs and Schultz's rule, actually have distortion that's about square root of the number of candidates. In 2017, Skyrman and Elkin showed that STV has distortion that's about logarithmic of the number of candidates. Even in 2015, in the original paper, Incelovich et al. Showed that it actually was possible to achieve constant distortion. So Copeland's rule achieves distortion 5, and this is independent of the number of candidates. And for a long time, this is actually what we thought may be the best possible. We weren't sure if it was possible to break this barrier of 5. And that was until a pretty amazing paper last year by Munigal and Wang. They introduced a brand new voting rule. It's slightly complicated, but it's really cool and actually it breaks this barrier and achieves distortion approximately 4.2. So an obvious next question then is, how much can we improve? And by now I'm sure you're wondering what a lower bound is. So again, in the original paper, Incelovich et al. Showed a very simple lower bound of 3. And this is actually the best one we know. And it's pretty simple, so I'll show it here. So in this instance, we'll only have 2 candidates, A and B. And half the candidates will prefer A to B, while the other half will prefer B to A. Now, this is a completely symmetric instance, so without loss of generality, let's assume our rule chooses candidate A. So what could go wrong? So let's assume that candidates are on a line here. And then half the voters are right about in the middle, but they ever so slightly have a preference for A. So these n over 2 voters here correspond to the n over 2 here that prefer A to B. The other half of the voters are at the exact same location as B. So they have 0 distance from B, well, approximately 2 distance from A. And these voters correspond to the n over 2 voters here that prefer B to A. And if you calculate the distances, you'll see that the cost of A is approximately 3 times more than the cost of B. So since this was without loss of generality, the voting rule can never have distortion strictly less than 3. And note that the problem here was that the voters that preferred A to B did so much less than the voters that preferred B to A, but there was no way for the voting rule to know that. So natural question then is, can we always achieve distortion of 3? And in this paper, we answer that. We construct a new rule that does, in fact, always achieve distortion 3. But before I can show you how this voting rule works, I need to introduce a different concept we introduced in this paper. This is the idea of a domination graph of a candidate A. So this is a bipartite graph with voters on both the left and the right. And there will be an edge from voter I to voter J when, in I's vote, candidate A weakly defeats the top choice of J. So I'll show you how this works by giving you an example. So on the left, we have the voters, and this is their rankings, and we look at where candidate A appears. And on the right, we look at the voters and their rankings and look at the top choice of that voter. So let's consider what edges are incident to this voter 2 on the right. So how do we do this? Well, we look at the top choice of this voter on the right, and that's this candidate C. And we look where candidate C appears in the rankings of voters on the left. And then we compare this to where candidate A appears. And in places where candidate A is weakly preferred to candidate C, we'll draw an edge. In cases where C is preferred to A, we won't. So this is the edges. And note that I use weakly defeat here. So that means we'll allow A to weakly defeat itself. It's like a greater than or equal to statement. And now we can do this for all the voters, and then we get this graph. So let me give you a bit of intuition about why this might be useful. It's a little long, so just bear with me. Let's say we want to choose this candidate A, and then we want to justify it to the voters. And so what could happen? Well, this voter 4 here could come and complain. He could say, wait, I don't like candidate A. I much prefer my top choice candidate, candidate B. And so what can we do? We can look at this graph, and we can see that from voter 4 on the right, there's actually an edge from 4 to 3. And we can say to voter 4, hey, look, voter 4, if we had chosen your top choice candidate B instead of our chosen candidate A, it actually would have made this voter 3 worse off. So, this is somewhat of a justification. And now this isn't a great justification. I mean, for a couple of reasons. First of all, why does voter 4 care about what voter 3 thinks? And second of all, this voter 3 is very powerful here, right? Since voter 3 prefers A as their top choice, no matter who comes and complains, we can always just hold up this voter 3 and be like, look, we would have made this person worse off. So this is no better than dictatorship. So let's make this a little harder on ourselves. Let's say once we've used voter 3 as justification, we can't use them again for a different voter. So in graph theoretic terms, what am I asking for? I'm actually just asking for a perfect matching in this graph. So the main technical result of our paper is what we call the ranking matching lemma, which shows that no matter what the rankings are, no matter how many voters and how many candidates, there will always be some candidate that has a perfect matching in their domination graph. So this is quite a technical result. It's the main heart of our paper. So I'm not actually going to go into the proof at all. But what we can use to, using this lemma, we can actually show this main theorem, which says that any voting rule that always outputs such a candidate has distortion 3. And we're pretty excited about this ranking matching lemma. And one of the really cool things about it is it makes this theorem actually really simple. And especially compared to lots of the standard proofs for distortion of other rules is pretty complicated. And I think it's easy enough that I'll show it here. So for this proof, let's fix a set of voters V, metric D, and let's suppose we choose a candidate A that has a perfect matching in their graph, M. Now let's fix some other candidate B, and where our goal will be to show that the social cost of A is at most 3 times the social cost of B. Since B was arbitrary, this will prove our approximation ratio. So as a reminder, what does it mean that A has this perfect matching M? It means that if we look at any voter I, and the voter that's matched with I on the right, voter I will always weakly prefer candidate A to this top choice candidate of the matched voter. So now let's do the proof. So let's start with the social cost of A, and then we can just expand it using the definition. Now what are we doing in this step? Well, this is just the definition of M. So as we said, for voter I, they prefer candidate A to the top choice of the voter matched with I. So what does this mean in the framework? It simply means that just the distance from I to A is at most the distance from I to this other top choice candidate. Now we can expand this simply using the triangle inequality. So replace with the sum from distance from I to B and then B to the top choice of M. What are we doing in this step? Well, if we look at this sum here, particularly this part, we see that we're simply adding up the distance from B, this other candidate, the top choice of the voter matched with I. But since M is a perfect matching, that simply means we're actually adding up distance from B to the top choice of each voter exactly once, right? Since M is a bijection. So since we're doing this, we could have just replaced it with the distance from B to the top choice of each candidate I. This will be adding up the same set of possible distances. we can then again expand this using the triangle inequalities to replace this distance from B to the top choice of I with distance of B to I plus the distance of I to the top choice. And then what are we doing here? Well, what does it mean for a candidate to be the top choice of I? It means they prefer it, at least weakly prefer it to every other candidate. So the distance from I to their top choice is at most the distance from I to the specific candidate B. And then using a symmetry of the metric, this is simply just equal to 3 times the social cost of B. And this completes the proof. And note that the reason this proof is so simple is because most of the complexity is hidden within the proof of the ranking matching lemma. So once we have the existence of this matching, we can use it in a really easy way to prove this distortion. So actually, when I introduced the ranking matching lemma before, I lied a little bit. That was actually just a special case of the ranking matching lemma. So here I'll show you the more general version that we think might be useful for other questions. So recall this is the domination graph of a candidate A. And note that for these voters on the right, we didn't actually care about their full rankings. We just cared about which candidate they chose as their top choice. So let's imagine that we replace these full rankings with simply the top choice candidate. And now in addition, note that when we constructed these edges, it didn't actually matter the identity of the voters. Really, the only thing that mattered was this candidate. So let's imagine that we replace these nodes simply a label of the candidate that was the top choice. And the next step is that actually if a candidate appears more than once over here, the edges that are incident of them are exactly the same. And that was just by the definition of the graph. So we could imagine instead that we combine these two nodes into a single one. So now this isn't really a matching anymore. It's more of a many-to-one matching. But we can think of having degree constraints on the right here. So to this candidate A, instead of having just one edge incident, we actually want 2. And we can also imagine that there's degree constraints on the voters here on the left. So in this case, it's simply 1 for each voter. And now in our more general ranking matching lemma, we actually allow for arbitrary degree constraints. So even real value degree vectors. And in this case, it's not really a many-to-one matching anymore. It's more of what we call a fractional perfect matching. But the general form of the ranking matching lemma shows that for any real valued voter and candidate degree vectors P and Q, no matter how many candidates there are or how many voters, or what the rankings of the candidates by the voters are, there will always be some candidate whose domination graph emits a fractional perfect matching. This is pretty cool because it actually introduces a new family of voting rules, one for each pair of vectors P and Q. For each P and Q, we can simply pick a candidate that has a perfect matching in this PQ domination graph. So in particular, for our proof of distortion, we use weights where for the voters P, it was equal weight for each voter. And the weights for the candidate was proportional to the number of times they appeared in the top choice. So I'm also going to show you one other possible interesting choice. So that's equal weights for all the voters and also equal weights for all the candidates. So in this case, what would this voting rule guarantee? Well, it says if we choose candidate A, we look at in any x fraction of the votes, this candidate A weakly defeats at least x fraction of the candidates. And this is true for any value x. And we think this might be related to an open question in social choice theory, which is known as the core. And at a high level, what the core is asking for is, for a given k, can we pick a set of k candidates such that on any 1 over k fraction of the voters, this candidate beats all of at least weakly defeats all of the other candidates. And we think these two statements are pretty similar, so it's possible this could be used to help prove that open question. So just to wrap up, in this talk and in the paper, we proved that the optimal distortion for deterministic rules was exactly 3. And as for some possible future work, as I mentioned, there's the connection to the open question of the core using the generalized ranking matching lemma. But there's also some interesting questions in the realm of randomized rules. So we proved this optimal distortion for deterministic rules, but it's possible that randomized rules can improve. the lower bound there is only lower bound of 2. And the best known rules, they prove that there's an upper bound of distortion of 3 minus 2 over m. But interestingly, these rules, as m grows large, they're no better than their deterministic counterparts. So a big open question in this field is, can randomized rules do better? Can we achieve strictly better distortion? And I think this is a really exciting line of work and some interesting open questions there. So that's it. Thanks for watching and listening.